Hi everyone, welcome to the talk on the lightweight inspection of data preprocessing in native machine learning pipelines. I'm Sebastian from the University of Amsterdam, and this is joint work with Stefan Grafberger from TU Munich and Stoyanovich from New York University. So our work is concerned with data management problems for machine learning. And as all of you probably know, we've seen astonishing progress in machine learning over the last years. So machines beat us humans now in more and more games like Go or Jeopardy that we saw to be our domain. There are widespread advances in computer vision. Facial recognition is used. There's expectations for autonomous driving. And in general, more and more decisions are being automated with machine learning techniques. And there's kind of a gold rush mentality and a machine learning arms race in industry. But at the same time, beyond the hype, there's also a set of serious technical and societal problems that are accompanied with by this machine learning hype. So on the technical side, something that our community is very well aware of, building real-world machine learning systems is still very, very tedious, and unfortunately, data preparation accounts for 80% of the work of data scientists. But beyond technical problems, there's also more serious societal problems. It is becoming apparent now that the automation of decision-making can also reproduce and amplify existing biases and discrimination. And there have been multiple examples for this in the media recently. For example, that facial recognition systems don't work as well for people with darker skin as for people with lighter skin. And our work tries to address some of these problems. So it is in the area of fairness and accountability. But first of all, I would like to say that this problem field is, in general, a socio-technological problem. So it's not something that computer scientists can solve on their own. And it requires collaboration with law experts and social scientists. And the responsibility for these decision-making systems can also not be automated. But what we can do is we can assist data scientists with some of the issues that occur. I think it's good to take a look at the different types of bias that can occur in these systems, in these automated decision-making systems. So there's pre-existing bias, which has its origin in society, which is dependent on the belief system. For example, whether it's fair or not to admit people to university just based on their grades, or whether you should also take some other socioeconomic factors into account. That's more a philosophical than a technical question. Then there is technical bias, the one that we focus on, and that's simply bias in the data that is introduced by technical systems. Maybe these systems filter out some data or change the proportions or the distributions of the data in some sense. And then there's emergent bias, which is basically arising from feedback loops once you deploy these decision-making systems in the real world, which is also very, very difficult to tackle. And in our work, we focus on the technical bias that is introduced in machine learning pipelines by data preprocessing. And the actual issues that can occur are numerous, and they can be very, very subtle. So for example, as soon as you join different data sets or you filter these data sets, there's always a chance that you accidentally change the proportions of certain protected groups in the data. For example, if you filter data by zip code, then there's a big chance that you change the proportions of demographic groups in the data because zip code is correlated with group membership here. And then there's also a lot of things that maybe machine learning people take for granted that can also take change these distributions. For example, if you apply missing value imputation for sensitive attributes like the gender. And in general, this is a very difficult problem for numerous reasons. So on the one hand, once we put data science and machine learning into production, we run into a lot of more organizational problems. So often machine learning experts design these models under some kind of lab conditions where they work on small, clean data samples, and often they don't really focus on data preprocessing. And then this code is handed over to some engineers, some non-machine learning experts who somehow puts this on production, maybe on other data, on new data. And it's hard to determine whether the data that is used by that model in this production setting is still representative of the lab data. Another technical problem is that there is no real algebraic foundation for data preprocessing in machine learning. So typically people glue together different technologies like Spark or Pandas or scikit-learn that use different data representations, that use different types of operations on the data. So it's very hard to come up with a principled approach to this. And another reason that this is a difficult problem is that we've also seen that even the experts can do it right. So in some work that we published at EDBT last year, we investigated some common machine learning frameworks for measuring fairness, and we found many violations of best practices in machine learning. So the question for our work is, can we help data scientists detect these problems? And can we actually connect this inspection of their pipelines to the actual data that is being processed? And in general, the inspiration for this work is coming from software engineering, where you have this very intelligent code inspection in modern IDEs. So modern IDEs give you a lot of hints. They see that you do dangerous operations, that you call deprecated methods. And kind of our vision is that we can also support data scientists with similar hints and inspections. So for this, we built the MLInspect library. And MLInspect is a library to instrument machine learning preprocessing code with so-called custom inspections. So the idea is that users can write these inspections, some user-defined functions, and we bring a lot of them with our library. And then MLInspect automatically applies them to the inputs and outputs of certain operations in the machine learning pipeline, in the data science scripts. And the core idea behind our system is that we want to work with native preprocessing pipelines. So we don't want to enforce people to use our own language or to annotate or manually instrument their code. We want to work with native Pandas or scikit-learn code with the restriction that it needs to be written in a certain declarative way. So Pandas supports a lot of relation operations where we know the semantics, and scikit-learn and also SparkML, for example, have these estimator transformer pipelines that are in some sense a declarative and logical way to express a machine learning pipeline. And we think of the machine learning pipeline as a data flow graph with certain operations, some of them classical relational operations, some of them more machine learning operations, from which we roughly understand the semantics. And MLInspect instruments all the function codes, the function calls in the data science script by investigating the Python AST. And then at runtime delegates relevant function calls to library-specific backends for inspections. So for example, we have a scikit-learn and a Pandas backend that know how to execute inspections on the inputs and outputs of the relevant operators. In the end, MLInspect returns this data flow graph that represents the program with the inspection results. And in general, we designed our library such that the runtime overhead is linear in the number of input records. And in the paper, we describe a set of use cases. So one use case is, for example, lineage tracking. So MLInspect allows you to propagate certain annotations per tuple through the DAG, through the program. By that, you can track the lineage of your records. You can sample intermediate outputs for debugging. And we also have automated tests for the distribution changes of protected groups. There's an example here on the right side. There's a simple filter operation on the county code, and you see that the proportion of the age groups in the data changes by that. So we have an inspection for that, and we could automatically determine that in your program. And in our paper, we have a complex example pipeline that's written natively in Pandas, scikit-learn, and Keras. And we highlight many of these subtle issues that can occur there. And we show how the corresponding data flow graph looks like that MLInspect extracts. And we show that all these issues can actually be pinpointed to certain operators where we can apply these inspections. We don't have time to go into the details, unfortunately. So thanks for listening. I hope this is interesting for you and you want to check out our paper for learning more. We have an implementation of MLInspect and a demo notebook for this example available online at GitHub. And the next steps that we will conduct are we want to implement backends for more libraries, for example, for TensorFlow Transform. We want to extend our instrumentation approach for also for distributed execution for frameworks like SparkML. And we want to do some studies how well this approach works on code in the wild that's maybe not written very nicely. So thank you very much.